Hello everyone, and welcome back to what I believe is actually the first physics video on the channel. So this will be fun, won't it? A little bit of lore on why there's a pineapple on the screen right now. Basically, I walked in the first block today, and I was like, we're all dressed in like Hawaiian stuff because that's the theme. What if I did like you know, like a Hawaiian tropical math problem? So my physics teacher, he said, well, it takes 3 seconds for a pineapple to fall from a tree, and it asked me to calculate the height of said tree, taking into account drag and all the rest. So yeah, let's do that, shall we? Getting started. We're going to be assuming Newtonian drag because I don't know, just because I don't feel like doing a Stokes drag. So we're just gonna have our force of drag right here. It's going to be equal to 1/2 times rho, which is the density of our fluid, as Wikipedia calls it, times our coefficient of drag. Whoa. So that should be a d in the subscript. Times our cross-sectional area times our velocity squared. If you throw in all the numbers here, what you actually end up getting is 7 times 10 to the negative 4 v squared, with appropriate units on the 7 times 10 to the negative 4, but you get the point. For just kind of brevity, I'm just going to call this k. Yeah, I'm just going to call that k. I don't feel like writing 7 times 10 to the negative 4. But anyway, so our net force on said pineapple, I guess I can draw a free body diagram. I'll make my physics teacher proud. Is we're going to have an mg going this way, and then we're going to have our force of drag going this way, basically meaning that F net, so ma, is going to be equal to, mg minus our force of drag, which is just going to be k times v squared. Now, if you actually Google, like, what's the mass of a pineapple, nothing comes up. But if you Google, like, the weight, it would be like, oh, yeah, it's like, 1,000 grams-ish. And I don't feel like dealing with any weird numbers. So we're just going to be like, yeah, pineapple is a kilogram. And also, by the way, we are assuming the pineapple is a sphere for the sake of this problem. It makes it a lot easier because I don't know how to calculate the aerodynamics of a pineapple. That'll be the sequel to this video, I suppose. But anyway, getting back on topic, that basically means that A is equal to g, force of gravity, which we will be assuming to be 10, minus k times v squared. This actually isn't that bad of a differential equation to solve. So yeah, let's solve it. It means v dot over g minus kv squared is going to be equal to, well, just 1, really. Meaning that, integrating both sides, I guess technically be a dv, I suppose, but like, you get the point. dv dt, meaning that rt right here is equal to this integral. Then we're just going to do a quick u sub, so we're going to say v is equal to, let's see, that should not be a 1, that should be a square root of g over k times hyperbolic tangent of like some variable. We'll call it x, I guess. Yeah, that's fine. It's a dummy variable, it doesn't matter anyway. Okay, so we have dv then is equal to the square root of g over k times hyperbolic secant squared of x dx. Which is actually quite convenient. And well, I say convenient, that is kind of the whole reason we did this u sub, or v sub x, I don't know, whatever you want to call it. At least that being so sarcastic, man. Okay, so what we have here is then the integral of the square root of g over k times hyperbolic secant squared of x dx divided by the reason we have this coefficient here, so that when we actually plug it in, the k's cancel and we can factor out the g. So you have a g times 1 minus tan h squared x. And you can just kind of prove this right here to be hyperbolic secant squared. of x. I mean, that's just hyperbolic trig identities. I'm not going to go into that in this video. In a future video, probably, because hyperbolic trig is quite fun, but not now. So now we have the integral of, I'm just going to, let's see, bring this out right here. So we have square root of g over k times 1 over g. I'll simplify all that later. And then we have the integral of, well, the secants cancel, so we're really just left with what, dx is equal to RT, meaning that we have our x is equal to square root of kgt. But one thing you might notice actually is, well, we kind of need to solve for x, don't we? So let's just do that real quick. Yes, so our x right here is going to be equal to, we are going to be going back and forth a bit between like velocities, so we're going to have to be solving stuff. No, this is what I mean. Square root of k over g v, and this, I did not write that out. I did not space it out properly. Oh my goodness. Very sorry. It's going to be inverse hyperbolic tangent square root of k over g times v. I'm just going to sub that in here. We are going to have, I guess, technically some constant of integration, but we're just going to assume that to be 0, because initial time is going to be 0, and also our initial velocity is 0, because the tree is not eating this pineapple, it is really letting it fall, although maybe we could, I don't know, maybe we could do something with a gust of wind, but let's not. Okay, so we have tan inverse of v is equal to, well, what's the coefficient up here? Sorry, that should be in there. Whoops. What's that? K over g. Square root, whoa, you wanna, okay. Square root of k over g, v is equal to the square root of kg times time. And then just solving for a velocity here, we end up having our velocity is equal to the square root of g over k times the hyperbolic tangent of square root of kg. I really thought that choosing k for that coefficient may have not been like the best choice, because that actually isn't a kilogram right there, but you get the point, I guess. Oops. Anyways, sorry. Yeah, so we found our velocity. So all we really need to do now is integrate our velocity from 0 to 3, because it takes 3 seconds to fall, dt, and this will essentially, well, give us our height. So, all we really need to do now is, well, just integrate this equation. So, what we're going to do is, let's see, square root of g over k times the integral of tan h of square root of kg times t dt. And I mean, this actually isn't as bad as it looks, but I mean, we'll still kind of work through it anyway. It's just gonna be a u sub. We're just gonna let u equal cosh. Yeah, cosh should be cosh, or kosh. I don't know how you actually say it. I should learn that. Okay. Du then is equal. I shouldn't write that down there. This means our du is equal to hyperbolic sine square root of our kilogram. That's not a kilogram. Square root, or times square root of our kilogram dt. And then just dividing both sides by that, we end up getting that times 1 over the square root of kg. It really is unfortunate that I chose KG. Let's just like double check that's right. Yeah, it looks right. Okay, cool. Meaning then that we have the integral of 1 over u du. Looks tangent, hyperbolic tangent is hyperbolic sine over hyperbolic cosine, meaning that, well, it simplifies to this, in that we end up getting, I'm just going to simplify the coefficients here, 1 over k times the natural log of u evaluated from 0 to 3 once we plug in actually this, so we have, well, u is just defined to be cosh, so we have natural log of cosh of the square root of kg t. And this right here is going to be evaluated from 0 to 3. And it's going to be our height. So luckily for, well, very luckily for us actually, if we plug in 3 here, well, we're just going to get a number, but I'm more interested in the 0. So if we plug in 0, you end up getting hyperbolic cosine of 0, which is just 1. Natural log of 1 is 0, so we don't really have to worry about this bottom bound, thank goodness. So this just means our height then is equal to 1 over k times the natural log of, or hyperbolic cosine of the square root of kg t. Sorry, not t, 3. I'll put that 3 out front. 3. And yeah, that should be our height. You know, it probably would be helpful to, you know, translate this into an actual number, wouldn't it? So, I have a Desmos pulled up with this, and what I got when I plugged everything in was 43 around 0.7 meters. And now let me just double check that with the calculator. I am very well aware that Desmos is a calculator, but also I just want to make sure that I'm not doing anything silly because, well, I have a history of doing silly math things, believe it or not. So I am just going to double check this. So cosh of 3 times square root of 10 times 7 times 10 to the negative 4, because that's our k times g. We'll remember. Okay, this is very interesting. Oh, my calculator. I got a very different answer on my calculator, didn't I? Oh my goodness. What's going on? Oh, this is very interesting, isn't it? Did I just like... Oh, yeah, because I used a 7 for that. Yeah, that's... Oh, silly me. Oh, silly me. Okay, yeah, it is that number. Cool. So... Okay, yes. So, if a pineapple falls for exactly 3 seconds, and we assume it to be a perfect sphere, with Newtonian drag, the height of the tree is about 43.7 meters, which is that's a rather tall tree. It's a rather tall tree, if I'm not mistaken. Now to put this in like normal, normal units for all of us in the U.S. to understand, that is about 143.37 feet. So quite tall. But yes. Anyway, this is just a quick little solution to how long it takes for a pineapple to fall from a 143-foot tree. So thank you for watching, and I'll see you in the next one. Thank you.